Hello everyone, good evening and welcome to today's session. So we will start the session. Today we are solving few questions are from 2013, 2011 and the question from 2014. So let's look at the first question for the day. The question is, the effectiveness of a heat exchanger in ENTU method is defined as, and which of the following option is correct? So there is a method named as NTU, that is number of transfer units, to calculate for the design of heat exchanger, where we say that the effectiveness of heat exchanger will decrease over time. So in that method, how do we define effectiveness of heat exchanger? That have been asked in the question. So basically in that method we define heat exchanger effectiveness as Q upon Q max, where Q is actual heat transfer rate and Q max is the maximum possible heat transfer rate from the hot fluid to cold fluid. So this is how we actually define this ENTU, effectiveness of heat exchanger in the ENTU method. So yes, the effectiveness we define it as Q upon Q max, and from the given question, so the first option is increase in the temperature of cold fluid upon decrease in the temperature of hot fluid. So this won't be correct. Similarly, actual exit temperature attained by the cold fluid upon maximum temperature attainable by the cold fluid, this is also incorrect. Okay, I might not have shared my screen. Okay. So let's start over again. So yes, as discussed, so we had to find the heat exchanger effectiveness by ENTU method. So we straight away define this effectiveness in ENTU method as Q upon Q max, where Q is the actual heat transfer rate, upon Q max is the maximum possible heat transfer. So from the given options, we can rule out the first three options, and the fourth option is correct according to our definition, that is actual heat transfer rate upon maximum possible heat transfer rate from the hot fluid to cold fluid. So you can straight away remember this formula for heat exchanger effectiveness based on this number of transfer NTU method, that is number of transfer unit method. So yes, here we define this heat exchanger effectiveness as ratio of actual to maximum possible heat transfer. There isn't any special concept in this, we just have to straight away remember this formula. Now let's look at the second question. So in the second question we have been given that in a pool boiling experiment the following phenomena were observed. The first one is natural convection, film boiling, transition boiling, and the last one is nucleate boiling. What was the correct sequence of their occurrence? And we have to select the options on the basis of their sequence in which they occur. So in the given question we have been given as P as natural convection, Q as film boiling, R is transition boiling, S is nucleate boiling, and we have to arrange them in the order which they occur. So here we have this boiling curve in much detail, in which there are different sections P, Q, Q, S, but this alphabetical order are different and we have to arrange them in alphabetical order. So in this pool boiling experiment, we have this heat source, consider a wire, and then we have a reservoir in which we have this fluid fill, and with the help of this wire we provide heat to this we provide heat to this fluid through which the boiling occurs within the fluid. So initially at the onset of heating, there will be the heat transfer would occur due to natural convection. That is, there won't be any effect of this temperature rise. So the first step will always be natural convection. Later on, as we move on to this direction, that is increase the temperature, then we can see all these kinds of graph. So let's look at this section PQ first. So here we have been given that initially when the temperature is slightly above the saturation temperature of liquid, the liquid in contact with the heating surface gets slightly superheated, and ultimately we call this as interfacial evaporation regime. So after this interfacial evaporation regime, what will happen is small bubbles will start forming on this wire. So that is the vapor. It is written over here. The vapor bubbles break and coalesces, thus an intense motion of liquid occurs, which in turn decreases the heat transfer coefficient or heat transfer rate or heat transfer flux from the heating wire. So this section QS is known as heat nucleate boiling. So in this boiling curve, this entire section is nucleate boiling, and prior to this entire section is natural convection. And after this nucleate boiling, we have been given that once the population of the bubbles reaches to maximum, the nearby bubbles coalesces and eventually a film of vapor forms on the heating surface. This layer is highly unstable and it breaks it forms momentarily and breaks, and this is known as transition boiling. So this region ST, in which few of these bubbles are formed, and we don't get a stable film of bubbles formed over here. These bubbles continuously form and break, due to which we call this as transition regime. So basically it is transitioning from nucleate to film boiling regime. So this ST region, we call it as transition boiling. And later on, this TU regime, in which we have this stable vapor film, and in this UV regime we have is known as this in this UV regime the excess temperature in this regime is so high that the heating wire may get melted, and this situation is known as boiling crisis, and we call this STUV altogether as this can be called as film boiling regime. So if you had to put all of this in order, so first will be natural convection, the second option is nucleate boiling, the third phenomena in the sequence will be transition boiling, that is third, and the last one is film boiling, it is fourth. So the order in which this phenomena will occur will be P, S, R and Q. Now from the given options we can select option D, that corresponds to P, S, R and Q. That is, initially there will be natural convection, and then we will be seeing small bubbles start forming, that is nucleate boiling. Later on these bubbles will grow in size and keep on coalescing and breaking, so there won't be a stable film of bubble, so that is we call it as transition boiling. And in the last section a stable film of vapor is formed over the heating source, and that we call it as film boiling. So that is option 4. So PSRQ is the correct answer. Now let's look at if you have any doubt you can write it in chat box, or we can move on to the next question. So let's look at question number 18 from GATE 2013. So in this question we have been given a hole of area 1 centimeter square is opened on the surface of a large spherical cavity whose inside temperature is maintained at 720 degrees Celsius. The value of Stephen Boltzmann constant is 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. Assuming black body radiation, the rate at which energy is emitted in watt by the cavity through the hole up to 3 digits after the decimal point is dash. So in this question we have been given a large spherical cavity. So let us consider this large sphere. So this is our spherical cavity in which the whole of this is our whole of area 1 meters if 1 centimeter square, that is 10 raised to minus 4 meter square, and the inside temperature is maintained at 720 degrees Celsius. So that is 1000 Kelvin. The value of Stephen Boltzmann constant we have been given as 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4, and we have to assume this system as black body and find the rate at which energy is emitted. So here we can use this correlation given by the Stephen Boltzmann, that is Q is equal to sigma A T raised to 4, where sigma is the Stephen Boltzmann constant, A is the area through which radiation occurs. So in this case, any ray of light that enters this body, let's consider this ray of light in this direction, so it will keep on reflecting within this black body, and ultimately it only has a single exit, that is from this hole. So from this hole only this black body radiation will get emitted. So the area we will consider this as the area of this hole, that is 1 centimeter square, and temperature is the temperature of this body, that is 1000 Kelvin. So we can calculate the value of Q as 5.67 into 10 raised to minus 8. Area we have been given as 10 raised to minus 4 meter square. And value of temperature is 1000 raised to 4. So this will become 5.67 10 raised to minus 12 into 10 raised to 12, that is 5.67 watt. So in this given question we had to find this up to 3 decimal points. So we will report our final answer, that is rate at which energy is emitted in watt, as 5.670. So this is our final answer. Yes, this is the final answer. Now let's look at the second question. You can speak up if you have any doubts, or just write it in chat box too. Okay, so if you don't have any doubts, we can move on to next question. So in the next question we have been given, in a double pipe counter current heat exchanger, the temperature profiles shown in figure were observed. During operation, due to fouling inside the pipe, the heat transfer rate reduces to half of the original value, that is we have been given Q2 is equal to Q1 upon 2. Assuming the flow rates and the physical properties of the fluids do not change, the LMTD in the new situation is, we have been asked to find the LMTD in the new situation. So we have the video solution for this, and we can take a look at that. I'm stopping sharing my screen. So we are looking at question 36. Let's play the video solution. we are solving question 36 of GATE 2013 chemical engineer. I'll just skip the question. Properties of the fluid. So let's look at the solution. So here we have been given a temperature profile corresponding to a counter current heat exchanger. So let's consider this as a double pipe heat exchanger. So tube side flow will enter in this direction, leave from this direction, and since we have been given the counter current flow, the shell side fluid will enter from this direction and exit from this direction. Now, and we have been given the temperature profile corresponding to that. So let's say the hot fluid is entering from 100 degrees Celsius and it leaves 60 degrees Celsius. The cold fluid will enter at 40 degrees Celsius and leave at 80 degrees Celsius. Now we have been given that during the operation, due to fouling inside the pipe, the heat transfer rate reduces to half of the original value. So let's say for case 1 heat transfer rate was Q1, and for case 2 heat transfer rate we have been given, it reduces by half, that is Q1 by 2 that we have been given. So assuming the flow rates and the LMTD in the given situation is this. So for this case we have to find the LMTD. Now let's consider this case 1. So the heat balance across this heat exchanger, we can write it as Q of total Q will be equal to Q of H is equal to Q of C, where Q of H is, let's just call this as the tube side fluid as 1 and the shell side fluid as second fluid. So it will be M1 Cp1 upon delta T, and delta T in this case will be 100 minus 60, and cold fluid we are denoting it by 2, so it will become M2 Cp2 upon 100. No, so for cold fluid we are having it as 80 minus 40, so that is 80 minus 40. So this difference is also 40, this difference over here is also 40, so we will be having M1 Cp1 is equal to M2 Cp2. So this correlation we are having. Now we will be doing it for the case 2, that is the fouling case. So for this case, let's consider the outlet temperature, that is the hot fluid outlet temperature, to be T dash out. Similarly, the cold fluid outlet temperature to be, so this was T1 and this will be T2 dash out. The inlet temperature of both this fluid will remain same. Okay, so this is cold fluid outlet, and over here we will be having the hot fluid outlet, that is T1 dash out. Now for case 2, similarly we can write Q is equal to M1 Cp1 upon 100 minus of T dash out. So this was the hot fluid, so it is T1. Similarly we will be having M2 Cp2 upon, for the cold fluid it is T2 dash out minus of 40. So from the earlier case we are having this M1 Cp1 is equal to M2 Cp2. So from this, we can get the relation between T1 out and T2 out. So it will become 100 plus 40 is equal to T1 dash out plus T2 dash out is equal to 140. Now we have to find a value of either this T1 out or T2 out. So we will find the value of T1 out. So from the earlier slide we were having we can calculate the value of Q. So Q will become mCp delta T, and for the second case, that is the fouling case, we are having Q2 is equal to Q1 upon 2. So using this correlation, we can write it as, for Q2 it will become m2 cp2 upon t2 dash 2 out minus of 40 is equal to m1 cp1 into delta t in both of these cases was 40. So that is m1 cp1, this will get cancelled out and we will be getting over here, so that is T1 dash out is equal to 40 plus 40, that will be 80 degrees Celsius. And similarly, from this correlation we will be getting T2 dash out as 60 degrees Celsius. So for the hot fluid the temperature will be 80 and for the cold fluid it will be 60. So if I have to draw this temperature profile for this new set, I can draw it as the inlet will remain at 100 degrees Celsius and the outlet temperature for this hot fluid is 80 degrees Celsius from over here. Similarly, the cold fluid inlet will remain same at 40 and outlet temperature is 60 degrees Celsius. So in this case, the delta T at, let's say, the hot fluid at this direct at x equal to 0 will be delta T is equal to 40 degrees Celsius, and over here also delta T will be 40 degrees Celsius. So since the temperature difference at both the inlet and the outlet are 40 degrees Celsius, the log mean temperature difference will be equal to delta T, that is LMTD. We will write it as 40 degrees Celsius. So yes, since both of these delta T were same, we didn't use that formula. It will be simply this temperature difference either at inlet or exit. So that is equal to 40 degrees Celsius. So the final answer is 40 degrees Celsius. Okay, so I will repeat that from case 2. I will repeat the entire question. So in this given question, we were given a counter current heat exchanger and the temperature profile were given. And for the case 1, we had this no fouling. And in case 2, we had considered the case of fouling. And for case 2, we had Q2 is equal to Q1 upon 2. Now Q1 is the heat across any of this hot fluid or heat change across any of this hot fluid or the cold fluid, so that we can write it as M1 C1 and delta T or M2 CP2 delta T. Okay, so where delta T is the heat change across this hot fluid or the cold fluid. For the case 2, the inlet conditions will remain same.
Sir, you are unmuted.
Okay. Am I not audible? Acha. So let's start from again. So for case 1 we had considered this no fouling case, and for case 2 we are considering the fouling case in which we were given this Q2 is equal to half of Q1. That is, over here the heat transfer rate reduces to half of the original value, and we have this value of Q1 as M1C1 M1 CP1 delta T is equal to M2 CP2 delta T, where, and for this case 2 the inlet conditions will remain same, and the outlet conditions we are considering, if we consider this hot fluid as first and cold fluid as second, so the outlet conditions here we are considering it as T1 dash of out, and for this cold fluid we consider it as T2 dash of out. Now we have to find this temperature T1 dash and T2 dash in order to find the LMTD. And in the first case we can see that for the first case we can calculate the LMTD as delta T1 minus delta T2 upon ln of delta T1 upon delta T2. So that is, we can get it from 20, so that we can later on calculate. And now we have to use this correlation to find the value of these outlet temperatures. So that is what we did in case 2. Okay, so from the first correlation we solved this heat balance equation, that is M1 CP1 is equal to 100 minus T1 dash out, and we got this correlation between this outlet, this temperature and this temperature, that is their sum will be 140. Later on we use this correlation where M2 CP2 and M1 CP1 will remain same. The outlet temperature we assumed it as T2 dash out, and the inlet temperature will remain same as 40, and similarly this will be equal to M1 CP1 and delta T, that was 40 from the earlier case. So that is, we got this T1 dash out as 80 degrees Celsius and T2 dash outlet as 60 degrees Celsius. And now we had to calculate this LMTD, and when we draw this temperature profile we can see that delta T remains constant, that is 40 degrees Celsius in both of this outlet and inlet temperature. That is why we can straight away consider that as 40 degrees Celsius. That is how we will get that. I hope that is clear, or else you can just take a look at the video solution later on. So we can move on to the next question then. So basically you need to calculate this Q1 from the earlier case and replace it over here, and then put this formula to find this T1 dash out or T2 dash out. Let's look at the other question. So this question is from GATE 2014, question number 47. So in this question we have been given that bottom face of a horizontal slab of thickness 6 mm is maintained at 300 degrees Celsius. So consider this a horizontal slab, and here the thickness we have been given as 6 mm, and the bottom face is maintained at 300 degrees Celsius. The top face is exposed to a flowing gas of 30 degrees Celsius, and then we have been given the thermal conductivity of the slab is 1.5 watt per meter per Kelvin, and the convective heat transfer coefficient is 30 watt per meter square per Kelvin. At steady state the temperature in degrees Celsius over the top faces. So we have to find the temperature over here, that is Ts. So we have the video solution for this, and we can take a look onto that. So this is question 47 of GATE 2014. of GATE 2014 chemical engineering paper. Yes, 0.5 watt per meter. So let's draw a general schematic. So we have been given a horizontal slab and the thickness we have been given as 6 mm, that is 6 into 10 raised to minus 3 meter. And the bottom face of the slab is maintained at 300 degrees Celsius. So this is 300 degrees Celsius and the top face is exposed to a flowing gas of 30 degrees Celsius. So let's just consider we have flowing gas over here and its temperature is 30 degrees Celsius. The thermal conductivity of the slab, that is K, is 1.5 watt per meter Kelvin, and the convective heat transfer coefficient, the H over here, is 30 watt per meter square Kelvin. At steady state, the temperature of the top face. So we have to find the temperature at this. So let's just call it as temperature at surface, that is Ts. So here initially we have been given the temperature as 300 degrees Celsius. And then we will be having conduction resistance over here, conduction R, that is R1, and then over the surface we will be having convective resistance, that is R2, and ultimately the temperature over here is 30 degrees Celsius, and over here we are having Ts, that is the temperature of surface. So we can write the energy balance as Q of conduction is equal to Q of convection. So where Q of conduction will be delta T for this conduction upon R1. R1 we are calling it as resistance. So for this conduction it will be delta X upon Ka, and for convection R2 will be 1 upon Ha. So that is R1, and for convection delta T upon R2. Now for this conduction the temperature difference will be 300 minus Ts, that is 300 minus Ts upon delta X upon Ka. So heat is being transferred in this direction. So the thickness through which it will transfer is this 6 into 10 raised to minus 3 mm. So that is delta X is 6 into 10 raised to minus 3 and into K. K is the thermal conductivity upon into area. So over this area the conduction will occur, and also this is the same surface area through which convection will also occur. So for convection the temperature difference will be Ts minus 30 upon 1 upon Ha. So the value of H and the area will be here. So this area will get cancelled out and we can replace the value of K as 1.5. So this will become 1.5 into 10 raised to 3 upon 6 into 300 minus Ts upon is equal to Ts minus 30 into value of H. We have been given it as 30. So this we can simplify as, so this will get cancelled out and we will be having 150 into 300 minus Ts is equal to 6 is 18 into Ts minus 30. So this will become 45,000 minus 150 Ts is equal to 18 Ts minus of 540. So you can solve this equation and you will be getting the temperature of the surface as 271 degrees Celsius. So we will report our final answer as 271 degrees Celsius. Do you have any doubts in this question number 47? Okay, so we can move on to the next question. So in the next question we have been given that oil at 120 degrees Celsius is used to heat water at 30 degrees Celsius in a 1-1 co-current shell and tube heat exchanger. The available heat exchange area is S1. The exit temperatures of oil and water streams are 90 degrees Celsius and 60 degrees Celsius respectively. The co-current heat exchanger is replaced by 1-1 counter-current heat exchanger having the So we are looking at this question 37 of GATE 2011, and the question is oil at 120 degrees Celsius is used to heat water at 30 degrees Celsius in a 1-1 co-current shell and tube heat exchanger. The available heat exchanger area is S1. The exit temperatures of oil and water streams are 90 degrees Celsius and 60 degrees Celsius respectively. The co-current heat exchanger is replaced by a 1-1 counter-current heat exchanger having area S2 if the exit temperatures and the overall heat transfer coefficients remain the same. The ratio of S1 upon S2 is. So here we have been given this co-current HE and counter current HE. For which we have been given this exit temperature as well as this inlet conditions. So these temperatures we have been given and they remain same across both of these cases, and we have to find the ratio of their surface area. So if the surface area of this co-current HE is S1 and surface area, that is the heat exchange area for counter current HE, is S2, then we have to find the ratio of S1 upon S2. So let's look at the video solution. So question 37, GATE 2011. Hello everyone, we are looking at question 37 of GATE 2011 chemical engineering paper. The question is oil at 120 degrees Celsius is used to heat water at 30 degrees Celsius in a 1-1 co-current cell and tube heat exchanger. The available heat exchanger area is S1. The exit temperatures of the oil and water streams are 90 and 60 degrees Celsius respectively. The co-current heat exchanger is replaced by 1-1 counter-current heat exchanger having a heat exchange area of S2. If the exit temperatures and the overall heat transfer coefficients are same, the ratio of S1 and S2 is dash. So in this question, initially we are considering the co-current cell and tube heat exchanger, for which we have been given the inlet temperature of the inlet and exit temperature of both the hot fluid as well as the cold fluid. Later, we are replacing this co-current heat exchanger by a 1-1 counter-current heat exchanger, and we have to find the correlation between the heat transfer area for both the cases if the exit temperature, inlet temperature and the overall heat transfer coefficients are same. So let's just consider first this co-current heat exchanger. Tube side will enter from here and exit from here. Similarly, the cell side fluid will also enter and exit from the same direction. Let's draw the temperature profile over here. So this is the hot fluid for which the temperature will decrease, and that we have been given as 120 degrees Celsius to 30 degrees Celsius. Similarly, the temperature of the cold fluid will increase, direction of both the fluid will remain same, and for the cold fluid the exit temperature, so the oil is used to heat water at 120 degree, oil 120 degrees Celsius is used to heat water at 30 degrees Celsius. So the inlet temperature of water is 30 degrees Celsius, and for the hot fluid it is 120 degrees Celsius, and the exit temperature we have been given as 90 for the hot fluid and 60 for the cold fluid. And for this case we are having the heat exchange area as S1. Now let's calculate the log mean temperature difference for this case. That is delta T LMTD for the first case will be delta T1. So delta T1 will be 120 minus 30 is 90, and 90 minus 60 will be 30. So that LMTD will be 90 minus 30 upon ln of 90 upon 30. So this will become delta TL1 as 60 upon ln of 3. Now we are replacing this heat exchanger by the counter current heat exchanger. So that is for counter current HE, the flow direction will be as mentioned in the figure. Tube side fluid will enter in the same direction, whereas the cell side fluid will enter in the opposite direction. And if I have to draw the temperature profile, then it will look somewhat like this. So this is 120 and the exit temperature will be 90, and for the cold fluid it will enter in the opposite direction. The inlet temperature is 30 degrees Celsius and the exit temperature is 60 degrees Celsius. And the heat exchange area is S2 for this case. In earlier case it was S1. Now we will calculate the log mean temperature difference for this case, that is delta T L2. So delta T1 over here will be 60 degrees Celsius, and at the other side it will be 60 degrees Celsius. So since this delta T is same, that is 60 degrees Celsius for both this inlet and exit, the log mean temperature difference we can straight away write it as delta T1 or delta T2, that is equal to 60 degrees Celsius. Now we have to find the correlation between heat exchange area S1 and S2. Now that is, we can, for any of this heat exchanger we can write Q as M1 Cp1 delta T. If this is cold for cold fluid, then similarly for hot fluid it will become M2 Cp2 delta T, and this will be equal to U1 area. Let's just consider it for counter current heat exchanger, so the area was S1, and delta T LMTD, that is delta T L1. Now for both of these cases, the cold fluid inlet and outlet as well as the hot fluid inlet and outlet temperature will remain same. The other parameters such as the specific heat and the mass flow rate are also considered to be the same. So basically for both of these heat exchangers, the heat exchange by either the hot fluid or cold fluid will remain same for both this co-current as well as counter current scheme. So from that we can write this as U S1 delta T1 is equal to U S2 delta T2. So here it is log mean temperature difference delta TL1 and log mean temperature difference delta TL2. The overall heat transfer coefficient also we have been given it as same, so that is U will remain same. So from this we can find the ratio of S1 upon S2 that is required in the question. S1 upon S2 is delta TL2 upon delta TL1. So basically it will become 60 upon ln of 3. So this will become ln of 3, and the value of natural log of 3 will somewhat around 1.1. So from the given options we can select the correct answer as 1.1. That is, if we are changing the scheme from co-current to counter current, then the ratio of their heat transfer area will be 1.1. So now look at, I hope this question was also clear. So in this question we found out that if the heat exchange is changed from co-current to counter current, then the ratio of their heat exchange area will be 1.1. So now let's look at the another question. So this is question 17 from GATE 2011, and the question is, consider two black bodies with surface area S1, where S1 we have been given as, for S1 the area is 1 meter square. For S2 we have been given that the area is 4 meter square. They exchange heat only by radiation. 40% energy emitted by S1 is received by S2. So that is, in this question we have been given that F12, that is energy emitted by surface area S1 and received by S2, we denote it by F12, and that we have been given as 40%. So we can write it as 0.4. The fraction of energy emitted by S2 that is received by S1 is dash. So we have been asked to find the value of F21. So from the reciprocity theorem we know that A1 F12 is equal to A2 F21. So from this we can replace the values of area and F12 and get the value of F21. So it will become 1 into F12 is 0.4 upon A2 is 4 into F21. So that is 0.4 upon 4 is equal to F21. So the value of F21 will be 0.1. So from the given option we can select option B. That is our correct answer. So now we can take a look onto the last question of the day. I'll just solve it over here only. So this is question 38 of GATE 2011, and we have been given that an aqueous sodium chloride solution is fed into a single effect evaporator at a rate of 10,000 kg per hour. It is concentrated to a 28% sodium chloride solution. The rate of consumption of steam in the evaporator is 8,000 kg per hour. The evaporator capacity kg per hour and economy are dash. So let's look at the solution. So here we have been given a single effect evaporator. So let's draw a single effect evaporator over here, in which aqueous NaCl solution is fed. Okay, so this is our feed, and in which we are feeding this NaCl solution of 10 weight percent, and the mass flow rate is 10,000 kg per hour. It is concentrated to 20 weight percent solution. So this is our concentrated product or the concentrated solution, which is 20 weight percent. We haven't been given the mass flow rate for this. The rate of consumption of steam in the evaporator is 8,000 kg per hour. So let's consider that steam is being provided over here and it will exit from over here. So steam we have been given as 8,000 kg per hour, and ultimately water will get evaporated or vaporized from this NaCl solution to leave this concentrated solution. So from the top we can write the water that has been vaporized. So that also we haven't been provided. This mass flow rate we haven't been provided, and we have been asked to find evaporator capacity. So first one is so evaporator capacity is the amount of steam that is produced. Okay, so that is the amount of water that is vaporized in kg per hour. And then steam economy, we define it as water vaporized, that is evaporator capacity, water vaporized upon steam that has been consumed to evaporate this solution, that is steam that is been fed to concentrate this solution. So steam consumed, so this we have to find. So we can simply do mass balance across this system and find the relevant quantity, that is the water vaporized. That is water vaporized, we require that. So in the feed we have this 10% NaCl solution. So 10% of this 10,000 kg will be 1000 kg. So in this feed we are having 1000 kg of NaCl and remaining 9000 will be water. 9000 kg we have this water. Now in this evaporator, none of this NaCl will go to the top stream, so all of this 1000 kg NaCl will be exiting through this concentrated solution, basically this stream. So in this 28% we are having 1000 kg NaCl. So basically that is equal to 20% of the total mass flow rate. If the total mass flow rate of the bottom product, let's call it as B, so it will be 0.2 of B. So we can get the mass flow rate of B as 1000 upon 0.2. So this will come around 5000 kg per hour. So since this is 5000, so in this case the remaining out of this 5000, 1000 is already NaCl and remaining 4000 will be water and 1000 kg NaCl. Now in the top we have to find the water vaporized. So this steam will not take part in any of this material balance correlation. It will just provide heat to the system. So this will at the exit will also remain 8000 kg per hour only. But we are feeding this 9000 kg water, and out of this 9000, 4000 kg of the water is being present in this concentrated solution, and remaining amount of water, that is 9000 minus 4000, will be the water that has been vaporized. So 5000 kg per hour is being vaporized from this single effect evaporator. So on the top, this 5000 kg of per hour of water is being evaporated. So that is evaporator capacity is 5000 kg per hour. And if we have to find this steam, this evaporator economy, so it will become 5000 upon total amount of steam that is consumed, that is given as 8000. So it will become 5000 upon 8000, that is 5 by 8. So this will come around 0.625. So the final answer we can select it as 5000, 0.625. So that is our final answer. So basically evaporator capacity is the amount of water that has been vaporized, and the economy is defined as amount of water that has been vaporized upon the steam that has been provided in order to heat that water, ultimately the steam that has been consumed. So this is how we find the evaporator capacity and steam economy. So do you have any doubt in this or any of the questions that we discussed today? We can discuss it or we can end today's call. This was our last question for the day. Do you have any doubts? If you don't have any doubts, then we can end today's call. Okay, so I don't think you have doubts, so we can end today's call. Thank you for joining.